class. So a few things some students just raised up. I think it's interesting, kind of also bring it up. So first thing first is if you're not able to make it to the class, this class particularly is you have a full excuse. But however, I think it's courtesy to let me know. So always let me know, either by email or through my students or anywhere, all right? Just let me know. So if you're feeling unwell, that's fine. You can just send me an email letting me know, saying that, hey, you feel unwell. That's it. I think I have no interest of knowing your privacy, but I think since you're registered for these classes, I do have the responsibility for taking your care and your safety. So just send me an email. I will not follow ask other related questions, all right? Second is about again, circle back about this term paper is that you're fine to use other already previous project you already wrote with, but you need to slightly change that. So you're more than free to use that topic to help you. You can think about this as also part of your thesis for writing your literature review. So either way, you still need to accomplish. All right, good. So let's get back to the topic of what I just wrote in the black over here. So what you're seeing right now, is a conversion diversion nozzle, and then there's seven cases. Actually, I just realized this is a typo. Modify this quickly. So this is subsonic. So SONIC, subsonic. Right, so there's SONIC. Right, so the 7 cases. First is no flow. Second is isentropic subsonic throughout, and then third is choke isentropic and supersonic flow. And 4 is normal shock to nozzle, and then normal shock to nozzle exit, and then 6 is overextend and underextend. So what is the catch of all of these cases? Each of these cases dealt with math formula. Actually, I have wrote it in my notes, but after contemplating, I decided that I won't actually write all these equations on the blackboard for the sake of your time, and since we're not doing fluid dynamic in this class, right? Although there's 7 places, but I want to particularly kind of give you some description of these cases, if it makes sense to you. Right? So first, no flow, meaning that there's no thing going on, right? 0. So whatever the P naught is going in is whatever the PB it is. So it's equivalent, all right? Second is isentropic subsonic throughout. There is multiple solutions that you can do this. In other words, is depending on how this conversion diversion nozzle dimension that you have designed, you will get a subsonic throughout for the entire input and output. So say if you have a subsonic flow going into the conversion nozzle, then you will also have a subsonic output, all right? So you won't have a subsonic go in and then supersonic go out, all right? Just to be clear with that. And this is particularly on second solution. The reason why you will have a subsonic is simply because the dimension that you design only limit to subsonic. Isentropic, again, is referring that there's no loss in heat due because of wear, fractions, and etc. Good. Third is choke isentropic. Choke isentropic. I missed something. Choke isentropic sub. Sorry about that. Sub. And so this is SCP and supersonic flow. Subsonic and supersonic flow. So that's 2 case scenario, again, depending on your scenario. When I say choke, meaning that 中文好像就是被卡死的意思嘛，对不对 ？choke. Now, when I say choke, meaning that at this point right now at your throat, choke is that particular speed reach Mach equal to 1. Mach equal to 1. Over here, Mach equal to 1. 所以就是音赫数达到1就是331 meter per second. So Mach equal to 1 and ACH equal to 1. So 331 meter per second. Okay, so this is at this flow will be the area that reach Mach equal to 1. And then you have two solutions. Again, depending on your conversion nozzles, you either have subsonic flow or supersonic flow, depending. Okay? Fourth is normal shock in nozzle. So this is a similar version on third places, is that instead, once you have a supersonic speed Mach equal to 1, instead in this conversion side nozzles, instead of maintaining that supersonic, it has a jump. A certain area, depending again how you design your nozzle, it will go into a subsonic speed. So say over here it is Mach equal to 1, Mach equal to 1, Mach equal to 1. At this certain point over here, it's suddenly raised into subsonic speed. Alright, so there's a jump. Okay, so this is a condition that we would like to avoid at all end cases. Okay, so we don't want to have a jump. 就跳跃式速度在你的喷嘴。So fourth is a normal shock in nozzle, and then fifth case is normal shock in nozzle exit. So meaning that again is particularly at the exit nozzle over here, you have a shock over here at just at this nozzle over here. Again, this is another case we want to avoid. And then 6 and 7 is the most common optimized way when you design your nozzle, over expanded flow and under expanded flow. These are the continued place where you see diamond thing going on, diamond shot outside your exit nozzle. All right? Does that make sense? All right, so these are the 7 cases. Yeah, go ahead.
7 cases we want to avoid.
So the cases we want to avoid is 3 and 4 and 5. Yeah, 3 and 4 and 5. I think you can also, if you want to avoid 2, that's fine. 2, sometimes people want to just have a solid flow, but normally when we design this nozzle, we want to reach a supersonic, right? Because you're designing, depending on what your end application is. If you want to do a commercial flight, you want to have an airplane F-16 reach a supersonic, right? So case 2 is something you want to avoid, right? So 1 is no flow, so that's, you don't want a no flow, right? You definitely want something flowing inside. So 1, 2, 3, 4, 5 is all the cases we want, and 6 and 7, right? Great question. So any other follow-up questions? No? All right, so let's continue on. Yeah, so case 6 or 7 is a common thing where you see these diamond shot coming out. Okay, that's what I was talking about. So moving forward, so when you deposit something, there is so-called deposit efficiency. This is very common when you do spray. So the main index for determining the percentage of particle deposit on spray is ms divided by mp. So ms is the particle weight and divided by whatever the feedstock powder is inside there. How much feedstock powder you have input, right? So a few things to give you an idea about the deposition efficiency for cold spray. Normally it's about 20%. So it's fairly low. Okay, it's very, very low. So think about this, like 80% of powder when you do cold spray is being kind of not deposited, being wasted. So that's something the sales of the agent doesn't tell you when you do cold spray, that you're actually wasting a lot of powder simply just to allow the powder to be attached onto the substrate. Okay, so the deposit efficiency is about 20%. Okay, Alright, second thing about the DE, the deposit efficiency closely largely depends on the critical velocity. So critical velocities is a common kind of thing, terminology that's being used in cold spray, you have to remember that when we're dealing with cold spray, is because that's the velocity that helps you bond the particle onto the substrate. That's the critical velocity, right? So you can try to use any pressure that transfer that pressure onto the powder to deposit onto the substrate. You can do any, like the maximum, right? But at the end, you want to do what's the minimum? Minimum, when I say minimum, it's the critical. What's the critical, right? You want to do the less effort of trying to deposit particle onto your substrate, right? So here comes along a author. I think my apologies, I didn't put the reference over here. So it comes along an author, and this is well known. This author has come up with this empirical equation that describes critical velocity for particle to be deposited onto the substrate. So over here is 667, meaning that is a particular particle he has designated. If I recall correctly, it's copper. So 667 is meter per second minus 0.014 density plus 0.08 Tn is the melting temperature of the particle minus T reference is whatever the particle you're using plus 10 to the power minus 7. UTS is ultimate tensile strength minus 0.4 Ti plus Ti minus TR. Yeah. So Ti means that is when you spray what is the initial temperature. So this again is an empirical equation. What does it mean by empirical equation? Meaning that there's no scientific or physical thing going along with all these equations. Simply it is a numerical thing that derives from a huge mathematical order, right? So there's no scientific thing going on. So what's interesting about this author, what he has done is that he tried to correlate with all the material properties and the processes around those and come up with this VCR, the critical velocity, that give people an indication of what is the minimum velocity for allowing particle to attach onto the substrate. So you can see that 667 is meter per second speed, right? So if you minus, mean that 667 decrease, right? That makes sense, right? And then you have plus, and then plus and minus. So what is the critical role of decreasing if you have a powder today? Say you want to spray aluminum, for example. So you want to say aluminum, you use this equation. What's the density of aluminum? About 4-ish, right? 4, right? So you put 4 inside, so the minus, right? So you put the density inside, this 667 decrease, right? And then what is the melting temperature of aluminum? About 600, right? So you put this, and then the reference, the temperature, right? Times 0.8. What's the ultimate tensile strength of aluminum? Then you times that, and then minus, right? So here's the takeaway. So whatever you subtract, meaning that your critical velocity decreases. Whatever you plus, meaning that the critical velocity decreases, right? So with this equation, it gives you some kind of idea what is the major determinant factor of increasing the particle velocity. Over here, you can see very clearly the melting temperature, right? If a particle that has a higher melting temperature, meaning that it requires more of an input of pressure, right? For allowing the velocity pressure, they are correlated, right? Allow the particle to be attached, right? And if it has a higher ultimate tensile strength, meaning that it requires more of an effort of particle attachment, right? Now, if it has a lighter density, meaning that it requires less of an effort of particle attachment to the subject, right? So this gives you an idea right now what this equation is describing with some of the physical meanings of today. Say if you're a cold spray vendor and I ask you, hey, I have say tin, 锡, okay, so 锡, tin is a relatively low melting temperature and has a very low ultimate tensile strength, right? So you can say that the velocity for allowing the tin to deposit onto the substrate is relatively lower than 667 meters per second, right? Does that make sense? Now, for example, if we have nickel has very high temperature, right? It's a very high temperature melting temperature. So plus, meaning that you plus under this value, increase dramatically, increase, right? So this kind of, in a very smart way or cunning way, that gives you an idea, right? So you might ask, well, I'm spending time talk about this with you is I think for each of the division, material, manufacturing divisions, or the graduates, I think it is you that at the end of your master's degree, if you can somehow tell the correlations that will really benefit the people to just again do try and error, because I'm the person who really hate try and error. And that every time my student report, oh, we have to do 1,000 or 1,050 or something process per hour, and this is the optimized. I really hate that. But with this, they give you an idea, so it's very, very smart. Right? And over here is a relationship between the temperature, pressure, and velocity of the gas. So here we'll talk about what defines Mach equal to 1. Right? So with that, let's go back to writing notes again. I have to apologize, I cannot use that. Yeah, so on the left-hand side, I'll go ahead and I already have wrote down what's the definition of VCR. You guys actually see. Here, you guys can see. So VCR, the VCR, critical, the very critical, and the V critical and its total differential can be expressed as a function of process and material problem. So over here, what I'm writing it down is going through how the author has come up with this equation to give you a Y scope. So basically what he has done is he has taken the process and material parameters and write into a function, right? Go ahead and then write this down, and then I have not finished writing this equation. So So, if you guys have time, you can find this paper and then, and I think really this is the way that you should read a paper, to understand what exactly is useful. Right? A lot of paper nowadays, it's more of an observation paper, right? But this is a tool. So on the left-hand side is what this author done is that he's assuming VCR can be a total differential that can express between the process and material parameter. So VCR, the critical equals to a function of A1, A2 plus AN. So A meaning that it can be a material parameter, it can be a process parameter. Okay, it's a function. What the author has done right now is he did a partial deviation. So DVR and then partial, right? Partial. So if you partial meaning that 在中文可以讲说偏微分或是做一点点的微分嘛 ，d 就是小部分。Okay, so if you cross the dA out, it's basically a left to what the dVR, right? So it's the same, it's just doing a partial, right? So over here, what the author has done is the maximum temperature at the interface. So he's assuming that there's a maximum temperature at the interface when the particle collide onto the subject. There is a temperature between this interface. I think that's understandable, right? And the impact, boom, there's heat between the interface, right? So the maximum interface, the Tmax is the key intermediate parameter. So assuming there's a relationship exists between Tmax and the process flow. So what he has done, what the author has done, is he incorporated Tmax within this function, Tf divided by the material parameter. So if you exchange that, if you put this, recalculate back, it's the same as this function. He's just adding the Tmax as a temperature between the interface, right? So if you bring back this equation back over here and do your partial deviation, you get VCR equals to VCR reference. So reference is today, this author has used copper as its reference particle. So I believe it's a 600-ish meter per second. Minus over here, these are all the material parameters. So depending on what AI, A1, A2, A3, what's the parameter, right? So I only listed a few, the yield strength, density, and modulus that's fit into these functions. And then comes along what we just see from the slide. There's a long list of plus, minus, different material parameters, right? So this is how he has defined the critical velocities for today, whichever particle expression you want to deposit. Does that make sense? Okay?
So, can I ask a question?
Yeah.
The number behind the MPA is 0, 1, or 0, only 1?
Oh, yeah, that's a good thing. I think it's 0, 0, 1. Yeah, 0.1, sorry. Yeah. This is 0. Okay. All right, any questions so far? All right, so another few. You guys, this is done, right? I'm gonna erase this. So another few things I want to talk about, the speed of sound in Mach number. What does that define? So speed of sound. Speed of sound and Mach. What does it mean by not Mach number? So what is the equation for that? and that's Mach divided by V divided by C, right? So that's speed of sound. Speed of sound. Yeah, so, I think it's worth to kind of, for you guys to write this down to somewhat give you an idea of what Mach defined, right? How Mach is being defined, right? So you can see on the left-hand side how the Mach number is being come up with, right? So over here, there's kind of 4 regions. So subsonic is Mach smaller than 1, meaning that when Mach is smaller than 1, you have a speed that's smaller than 331 meters per second. Does that make sense? Okay, and then you have transonic, Mach equals to 1, and supersonic, and then hypersonic. 1, higher than 1, and then higher than 5. Okay? So a few things is, over here, I'm using C equals to radical K RT. K over here is CP divided by C CP.
可是空气有比热有那么大？
到1.4。
哦，1.4吗？哦 ，OK，
Yeah, so the ratio over here I'm assuming is 1.4. So the ratio over here is 1.4. So once you know the ratio of the air ratio 1.4, you put in 1.4. R over here, so this is just really the units. R equals to 287 joules per kg K. So sometimes R, as you know, sorry. So R over here, sometimes you can, there's different unit for that. The most unit you know is 8.314，八点三四 K per mole。但我是因为这个单位不太一样 ，the unit is a bit different, so I changed. And then once you bring in the number inside, you calculate C equals to 331. So this is how C is being come upon. So now whatever the measurement right now from the object you're measuring, once you put into V, you calculate if it's higher than 331 or lower than 331. Now I also stated over here below C equals to V radical R T divided by MV. So depending on your medium, if it's a monatomic gas, meaning that like it's just pure nitrogen or pure argon, it's not. So air, there's a mixed ratio, right? There's 空气、氧气、氮气是这样。但是 if it's a monatomic, meaning a single atom, the R ratio change. The C, when you put it, you also have to consider the molecular weight is different, right? So then your C might be different. Right? So anyway, the important thing is the right hand side is when people say about supersonic, meaning that the speed is higher than 331. All right, is that clear? All right, you guys get with the notes. I need to still give you a few seconds. Alright, so a few things I want to still add on and then we can call it a day for today. Alright, you guys good? Alright, I'll still leave the notes up on the board later on, but I need to proceed. Let's move on. So I'm gonna give you some glimpse of what the cold spray machine, maybe for the next time when I come up and talk about cold spray, I want to definitely show you some videos. So these are the low pressure cold spray and the process problem I'm going to go into and cold spray properties, morphologies and features, right? So there's many ways you can measure the particle velocities when I talk about velocities every year. So how the heck do you measure your velocity, right? How do you do that? I mean, you know the pressure can come from the pressure gauge, right? So one important device you can do is build up a system on the left-hand side of here I provide, so that help you measure the particle velocity. So particle velocity is critical, right? We spend one class is explaining the critical velocity, right? So this is a mechanism where this is a closed rate nozzle in the machine, the console where you control the temperature and pressure, and then you have the cylinder, right? So what it does is you have a particle shooting into this is a tube plate that's attached onto a motor, right? And on the first plate there is a nozzle, there is a notch over here. So while this tube plate is rotating, this closed rate powder is continuing injecting powders, right? While this particle goes through this notch, it's continue flying while this tube plate is rotating, and it is with the angle differences that allow us to calculate the particle velocity. You guys understand this very fundamental, very easy physics. So with that, we're able to calculate this angle with this equation. So this pi in the end is the rotation velocity, the RPM. S naught is the plate distance, and C value is the angle differences, right? The angle difference. So over here is each of these angle differences that I have measured that we're able to calculate for particle velocity. So over here, now very nicely, this is the inlet pressure that usually when I talk about for cold spray that you put inside the system, and then you can measure the particle velocity exponential increases, right? So there's many ways you can do. You can use a high-speed camera, you can use a laser adapter to do such a thing to do. But one thing is, I think this is a very kind of a very cunning or very easy stuff you can build in your lab to measure the particle velocity. All right, so quickly. All right, so another few stuff going along. I think this is very common when you start doing literature review. There's a lot of jargons and terminology thrown at you, such as what's the particle size distribution? How do you read the particle size distribution? What is the particle probabilities, the mass flow rate? So to give you a glimpse over here is you can see these are the particle size, different particle, lumen, copper, tin, this is from the SN images. And this is a very common terminology you can see is the particle size distribution where we categorize as E 0.1, 0.5, and 0.9. So 0.1 meaning that it's at the 10% of your distribution, while 50% is the medium and 90% is at the 90%. So I think when you read these particle size distribution from the particle size analyzer, sometimes it might be a little bit tricky just reading these data because you're assuming this is a normal distribution, right? Normal distribution. So you have something like this, you have a distribution, right? 正常分布嘛，对不对？所以在50%的都是一个50%嘛，然后10%是这样，然后90%， 90%, right? So you're reading. So when I plot this, you assume this is distribution. But sometimes powder isn't like this. A lot of times you'll see powder that have like a camel peak like this. And what it does, if you do this, if you just look at the 10 and 50, 90%, is it's going to give you 90%. It's going to give you 50% of this. And then 10% over here, and then 90% over here. Okay, so I think it's very deceiving. Sometimes you just read these numbers. It's always good to plot the number out. So be careful when you read the papers. Over here, there's the powder flowabilities. Sometimes when you read a lot of articles in particle technologies and stuff, there's how do you quantize powder? So it's basically by putting powder inside a drum and allow it to rotate and measure the angle. So this is fairly easy. This is also according to a standard, ASD standard. You can easily think about if this particle today is circular, right? And then you put it into a drum and continue to rotate, it's easily kind of float down, right? So the angle over here is slightly lower. While if you have a particle that has a higher resistance, it's difficult to rotate. All right, so that's a drum thing. And particle velocity over here, as I mentioned. So I won't get into detail about all of this definition, but you can see from these results over here, I'm showing is, you can see that axis is the input pressure, y-axis is temperature. So the catch about these is when you do a lot of these spray is that when you fix on a certain process parameter, the output of these velocities is very, very different depending upon what particle you're spraying, right? So I think this is by evidence you can see these colorful gradient that I'm showing is the particle velocity, right? So at a fixed parameter, each of these results are different. The particle velocity is very different. So again, is that don't assume that if you fix it on a certain process parameter, the output is going to be different if you today input a different materials. Does that make sense to you guys? Does that good? You guys familiar with that? So we have tin, aluminum, copper, and aluminum. You can see these are, for example, over here, the colors are very different, right? All I'm doing right now is just different powder, okay? So not to say if we change different morphology and size distribution is very completely different. So I think it's good to say that when you do experiment, regardless today it's using cold spray, right? Like one single change of your parameter, everything changed. I guarantee you that, right? So again, this is the mass flow rate, how much powder that's coming out from the nozzle. So mass flow rate, so these colorful diagram basically is defined as the mass flow rate, meaning by a certain amount of time, how much powder that has come out from the nozzle. So you can see from 4 different powders, right? You can see the color gradient is very different, right? So the more easier of the powder that can flow, the more powder that comes out, the more difficult of particles that are less flowable is difficult to come out from the nozzle, right? So you might ask that, hey, Professor, why not we have more powder coming out? Great, more efficiency, right? That's not true at all, right? Because sometimes if you have too much powder coming out from the nozzle, you have stagnation inside the nozzle, okay? So there's always the balance that when you design these kind of stuff. Does that make sense? Good, right? All right, so this is the power of substrate interaction simulations. Over here, I actually plan to talk about what plasticity is. When we do the class over, it's 4:20, right? All right, so we'll pick up over here, we'll talk about more about plasticity because this is another like a 2-page of notes. I want to talk about what plasticity is. So when you do simulations, there's always, when you do these kind of simulations, so what we're seeing about here is a aluminum and a substrate is the iron, right? So there's always the elastic part and the yield part and the ultimate tensile strength and the field part, right? The fracture part, right? So when you do simulations, right, there's a key, there's always the key things that you have to think about, right? So over here, below over here, this is the elastic region, right? So these, usually you need to know the modulus of the material. That's the material around, right? Over here, starting from over here, this yield point, this is the plastic region. So usually when we describe this plastic region, there's multiple equations that we can describe. There's no particularly, they're mostly numerical. They're not scientific stuff. So Johnson-Coulter is one that describes this over here, that describes this loop over here, okay? And then over here is the fracture criteria. So there's 3 important things, the modulus, the plastic deformation equation, and the fracture criteria. So do you want to break over here, or break over here, or break over here? That's the fracture criteria. So when you do simulations, there's the 3 important criteria you need to think of, which we're going to talk about for our next lecture. Any questions so far? All right? So, if not, we'll call it a day today, and then I'll see you next week. So next week, we'll have an invite guest that talked about additive manufacturing of ceramic material, right? All right, so if we don't have other questions, I will see you next week.